the tire webinar that we are presenting today at IDIADA, from physical testing to virtual tire vehicle integration. I am Joan Puig, Tire Development Product Manager, and we would like to present you some experiences that we have had during these last years in IDIADA in the field of tire development. I would like to explain you also how we are going to deal with this webinar. At the end of the presentation, we'll have some time for answering your questions that you will need to put it on the chat. We'll register, and at the end, we'll have some time for that. This webinar is registered, so you will have access at the end at any time if you want to review any point that you have been explaining. Now, let me present you our tire team. I would give the voice to our members. So please, Pierre Thibodeau, could you present yourself?
Hello everyone, so I'm Pierre Thibodeau, responsible for tire testing in IDIADA.
Then Carlos Fidalgo.
Hello, dear engineering colleagues. My name is Carlos Fidalgo, and I am CA engineer in charge of tire projects involving tire FEN modeling. Thank you for joining our webinar.
And then Imanol Laraudo.
Hello, everyone. I'm in charge of tire modeling in IDIADA. Nice to have you everyone here. Thank you for attending. So the main topics we will go through in this webinar are the following. We will do a quick introduction of our company and our services. We will go through our testing and analyzing tools, as well as our modeling capacities. We will show some of our experiences we've had during these years, and we will also show the future projects we are working in, and finally we will do a conclusion as a wrap-up of the webinar. At first, we would like to do a brief introduction of our company. As you may know, IDIADA is an engineering partner to the automotive industry, which provides complete solutions for product development around the world. As you can see, some of our main assets are the following. We are a team of more than 2,000 professionals with first-class state-of-the-art testing facilities. We have an international presence in more than 23 countries. And one of our strong points is the use of innovation in our services and technologies. In the following slide, you can see all our services related to tire development. As you can see, we have two kinds of services regarding tire. One of the services focused on vehicle, and such as subjective evaluation, braking test, aquaplaning test, dynamic test, also durability test, MBH, and also rolling resistance and fuel consumption. And regarding just the component where we will focus today, we have tire characterization and modeling we perform in-house. In this slide, you can see our background since we started our tire product, or the evolution. Everything started with the purchase of the skid trailer. It was in this point when we decided to bet on real proving ground conditions for tire testing, because we think it's very important to test your vehicles in the same surface as you will test your component. So then correlations might be easier than using laboratory testing to match your vehicle tests. From this point, we started winning different projects and developing different services until nowadays. But the most important thing of this slide is so you can see that we are always improving our testing and modeling capacities every day. And now I will let you with my colleague Pierre, who will introduce our testing and analyzing capacities.
Thank you, Emmanuel. So, as my colleague Emmanuel just said just before, IDIADA is a company which can offer you a complete support during the development process for each part of a vehicle. But today we will focus on tire. In IDIADA tire department, the first and main goal is to help our customer to integrate the tire on its vehicle on the best way. For that, we are using several tools, which I will introduce now. So the first of them is the skid trailer. This machine permits us to characterize the tire on dynamic condition on a real proving ground. The tire is fixed to a hub on the center of the trailer and can be controlled in different ways: slip angle, camber angle, vertical load, etc. While all the forces and movements are recorded. Thanks to that, we can determine several characteristics of the tire, like the cornering stiffness, longitudinal lateral maximum adherence. And one of the advantages of a trailer compared to a flat track is that we can move it to other place and so perform the test wherever you want. For instance, 2 years ago, we made a snow campaign in Sweden to compare the characteristic of a tire on dry and wet condition, test performed in IDIADA proving ground, and on snow condition, test done in Sweden. And the second one is the KC rig that we have modified and adapted in order to be able to use one of the platform to test just tires. The machine permits us to characterize the tire on quasi-static condition. The platform that you can see in yellow in the picture can be controlled on 5 different axes: X, Y, and Z displacement, and X and Z rotation, while the 6 forces and moment are recorded. Thanks to that, we can determine the longitudinal, lateral, rotational, and vertical stiffnesses of the tire, but also perform complex tests like parking maneuver. In this case, the used surface is a 3M P120 sandpaper, but we can adapt to it any specific requests from customer. For instance, we are currently working internally on the adaptation of a block of asphalt to have test condition as real as possible. Last but not least, the drum machine. As for the KC rig, we modified and adapted a drum made for rim testing in order to characterize tire frequency response. The tire is rolling on a steel drum with a clip, while the center of the rim is fixed. As for the other machine, all the forces and moments are continuously recorded during the test. Thanks to those tests, IDIADA can determine the frequency response of a tire to different excitation, different clips. This rig permits to make a big step on the modeling process, mostly for F-tire model that is a physical model. In order to use properly those 3 rigs, IDIADA developed internally a set of test lists to characterize as well as possible the tire, considering its own temperature and wear, but also the climatic condition. For that, each test list is adapted for each tire in order to match perfectly each behavior. Moreover, IDIADA is open to any specific request and have the capacity to study updates on test rig and test process. For instance, last year, a new test procedure has been developed, modifying the software of control on one of our rigs. In parallel to the testing tools, we developed internally, hard work on definition of post-processing and analyzing is done. Dynasoft Tyre, some picture of example you can see on this slide, is an in-house software developed to answer to the specific issue of tyre testing and analyzing. It permits us from the simplest conversion of raw data files to a standard format like TDEX, to a complex analysis of the test calculating metrics which characterize tires. It integrates also a simple fitting tools based on passage car formula. But why are we performing such analysis? But for example, to compare tires between them or to reference one during a benchmarking project, for instance. For that, a set of different normalized metrics has been developed to characterize a tire in order to be able to compare this data with control conditions. These tools helps a lot the customer when they need to make the first choice of a tire or when they want to integrate them on their vehicle. It also helps tire manufacturers when they need to compare different prototypes to define the line they need to follow for the development. So until now, we talk about tire characterization, but there is another interesting topic to deal with, the proving ground characterization. As explained before, the skid trailer is performing tire testing on real proving ground. In this case, in the case of using a reference tire, there is a possibility to characterize the proving ground, performing longitudinal tests based on different regulations. As for all the other topics, IDIADA is used to work with some of them, like you can see in this slide, but is open to study new one if the customer requests it. To resume a little bit, IDIADA has a wide range of testing and analyzing capacity, which are in a continuously improvement process based on investigation, but also on customer requests. As explained on the last slide, all the tests and analysis done help the final user to understand better the tire during the vehicle integration or prototype process, but is not the only usage. Based on all of this, models and virtual simulation can be done, and my colleagues Emmanuel and Carlos will explain a little bit more about that now.
As my colleague Pierre just introduced, we will go through our modeling capacities. We will start with magic formula models, which are mathematical models based on Pacheco equations. We actually perform different models, such as magic formula 5.2, which has two different use modes, use mode 4 and use mode 14, which includes the transient behavior of the tire. We are also able to build magic formula 6.1 models, which is the main model used by IDIADA. We strongly recommend this model over the 5.2 because it has better things such as pressure behavior. This model includes 3 inflation pressures. The transient effect is also better, which is similar to Swift model. And the camber description in this tire model is better than 5.2 model. All these models are mainly used in-house for handling simulations. these models are generating two different kind of tests, tire dynamic test and tire quasi-static test. Regarding dynamic test, we perform pure lateral test for studying lateral force and MZ torque. Regarding slip angle, we also perform pure longitudinal test, which we focus on longitudinal force versus slip ratio. And the last dynamic test we perform is a combined test, which is a mixture of lateral and longitudinal test. So while the tire is rolling with slip angle, we perform some braking test to see how the tire is behaving in different conditions. Regarding quasi-static test, we perform tire stiffness tests such as vertical, lateral, and longitudinal test, and we also include some footprint test for Magic Formula 6.1 for the transient behavior. In this slide, you could see how our model generation process is. As I said, we start with dynamic and quasi-static test with all this experimental data from our test. We perform the fitting of the model in order to obtain our tire model. As my colleague Pierre introduced, we have the possibility of building this magic formula test on different surfaces. We did a project which included dry, wet, and snow conditions for the models. And what we did is directly test on these different surfaces, because it's representative of what is happening between the surface and the tire. Using these three surfaces gives us a better fitting for using our models in car simulation. We also have the possibility of testing in our clients' proving grounds. And what we saw during this project is the usage of scaling factors which weren't used, because as I said, we tested on the surface the vehicle would be tested. So we used just the raw data for obtaining all these three models in different surfaces. The one thing to say about scaling factors is that they could be really helpful for the general behavior of the vehicle and could give you some hints on where to improve. But we saw that for testing in different surfaces, there is no rule to use the same scaling factors, because the tires are so different that it's not possible to use like standard scaling factors for obtaining the behavior of different surfaces. Regarding Magic Formula simulations, we have an internal close collaboration with our simulation team, which gives us the possibility to validate the models with complete vehicle simulations, and also have a good knowledge of several simulation softwares, so we can adapt our model to every of all the softwares there are. Now we would go through our physical modeling, which includes F-tyre modeling. For determining the tyre characteristics of this physical model, we start by doing some footprint tests in static conditions, as well as static measurements, such as tire stiffness and basic tire properties. Then we also include some handling tests that are performed in our proving ground with our skid trailer. And we normally include pure lateral and pure longitudinal tests. And for determining the frequency response of our tire, we perform some clip tests in our drum machine, rolling the tire over a clip in order to determine this frequency response. Here we have some specifications of the F-tyre models. The F-tyre model is a physical model which is available for using it on real time. It is able to simulate up to 250 Hertz. This model has a better behavior in terms of comfort simulation, and it also offers us the possibility of simulating thermal behavior. These models have extra capacities and vehicle handling simulations, as well as tire durability simulations. One of the strong points of this model is ride and comfort simulations, which offers us the possibility of simulating in unstable surfaces. It also gives us the possibility of using any virtual proving ground, including our proving ground in Spain. And as I said in the beginning, it also gives us the possibility of performing some real-time simulations. So regarding the model frequency ranges, as we saw in for the moment, we explained two different tire models. If we would like to test in low frequency, we will use Pacheco tire models. If we would like to go up to 250 Hertz, we will go to tire structure models such as F-tyre. And if we are interested in going to higher frequency ranges, we would use our finite element models, which my colleague Carlos will go through and explain.
Thank you very much, Imanol. Finite element analysis models of a tire are key for understanding the different performances of the component. As we know, the tire in service withstands many and uncertainty loads, like, for example, rim mounting, the inflation pressure, the car vehicle weight, sometimes crash impacts, or sometimes we run the tire over obstacles. So this uncertainty, together with a very complex composite structure composed by 14, 15 rubbers, nylon plies, steel cords, and beads, makes to build a tire model a very complex task. But even with this level of complexity and the fact that actual methodologies sometimes, or by the moment, will not reach in a quantitative way the exactly behavior of the tire, we actually believe that to have a good tire FE model is necessary for a proper understanding of the tire. Studies performed with these models will lead to reduce the number of prototypes that do not match the requirements for a good performance, avoiding manufacturing many of them and saving a lot of money with that. But of course, testing cannot be replaced. And these are the reasons why in 2015, through internal research projects, we developed a series of tyre models which cover a wide spectrum of tyre performances. First models we work on, which are the base of the rest, are the structural models with which it is possible to calculate the static behavior of the tyre, stiffness in the 3 directions, and also perform handling maneuvers, including braking, acceleration, cornering, and their combination. The second group would be the dynamic models for calculating modal and frequency responses, and for example, also the response of the rolling tyre over an obstacle. For vehicle development and to integrate the tyre models within the whole vehicle model, simplified tyre based on dynamic advanced tyre models are used. And the main objective here are the body-in-white comfort, durability, and rolling noise calculations. Also, tyre for dynamics for abuse and crash load cases can be calculated. A special case would be, for example, a small overlap crash test where the tyre behavior is key for understanding the intrusions or for performing intrusion studies in firewall and APLAD. And of course, for electrical vehicles, tyre noise is the biggest contribution for a wide spectrum or wide range of service velocities. So it is important also to know the relation between tyre structures and the radiated noise, and how is the perception of the radiated noise by the passengers and pedestrians. So noise propagation models helps with this task. As example of all these models, I will show the dynamic model for obstacles scenarios. 2017, we have the experience of comparing one tyre dynamic model with the tyre rolling in the drum of the Leonardo machine at different speeds, vertical loads and inflation pressures. So free rolling was tested, but also we run the tyre over obstacles like you see here in the videos over one cleat. As you can see on the right side, the frequency response in the 3 directions correlated quite good, but still there are some differences in amplitude and frequency in the response. So this response is affected mainly by the material rubber characteristics. So performing a proper rubber material model in terms of hyperelasticity and viscoelasticity is our main objective if we want to have a ready model for being included in a tyre development process. And it leads us to the question, what do we need to calibrate the rubber material properly? And the answer is to know the modes of deformation of the rubber. In the 30s, it was thought that only with uniaxial test, the rubber behavior could be completely described. But what do you think? Was it correct? What do you think? Does it fit the rubber behavior? So many of you have thought that no, it is not correct. No, it is not enough. And this is the answer. It is not enough. So rubber are anisotropic materials, which means that they have different responses according to the direction of the applied forces on the specimen. And this is why some other tests are needed to define completely the rubber behavior. And these tests are the equiaxial or compression test for uniaxial compression strain states characterization and the planar tension test for the pure shear deformation mode. So at the end, the objective is to perform several tests virtually and fit it with experimental curves with an advanced material model. In the graphic, we see the results of a uniaxial test at 3 different strain levels, red, blue, and purple, and by several loading and unloading cycles. So the phenomena to be described by an advanced material model are, first of all, the strain state by the first load applied that represents the virgin state of the rubber, where we can observe the nonlinearity of hyperelastic material. If we focus now on the purple line, which represents the 3rd strain level in this test, we see that for the second load applied and the successives, there is a sudden softening of the material. This effect is known as Malin's effect. It is a damage phenomenon based on maximum strain level that the material has been exposed. And also, hysteresis loops can be observed in these loading and unloading cycles. So in addition to this phenomenon, we know that for simple equiaxial and planar tension tests deliver different curves. So for an advanced rubber material model, all these phenomena at different strength level for each of the modes of the deformation should be fit. For defining the material model.
Let me stop you because we have somebody who is handing the hand. I would like to remind that the questions will be answered at the end. So please send questions to our chat, and at the end we will answer all of them. We can revise any slide at the end, no problem. But just we leave the questions at the end. Sorry, Carlos, for this.
Okay. No problem at all. So, as I said, for defining the material model, very condensed guidelines of an approximation to the rubber material calibration task will we explain now. Okay. So for a material model definition, the basis of the calibration will be the hyperelastic model for large strains calibrated based on the virgin response. Several models exist to define this nonlinear behavior, like for example, Yeo or no hook. Then we can add the viscoelasticity behavior, time or frequency dependent, based on relaxation test. And the viscoelasticity definition can be linear through Prony series, for example, or non-linear and temperature dependent with parallel radiological models. And also the Malins effect can be captured using Outen-Roxburgh model, which includes hysteresis behavior. The integration of all these phenomena leads to a wide amount of model factors to be calibrated. And some of them, they don't have a very big effect in the response. So it is neither easy to deal with a big amount of factors when performing, for example, sensitivity analysis, which is the main goal with this. So through a preliminary DOE, key factors for the rubber response can be discerned. And after that, a second optimization loop can be again performed, but by maintaining constant the factors which don't have a big effect on results. And for example, when additives are changed in the rubber compounds, the hardness of the rubber changes. And results show it is possible to parameterize the material model parameters by means of A shortness in a linear, piecewise linear, or exponential way. And after this step, after this parameterization of the material model parameters, the model parameterized with A shortness can be calibrated and can be used in the tyre model, which will be included in the tyre development process, and sensitivity analysis can be performed. So this was for tyre development, but tyre behavior importance is because of its symbiosis with the vehicle. So tyre must be included for complete vehicle development process, and here the approximation change. By the vehicle development process for performances like comfort, fatigue, or rolling noise, there are sometimes lack of information regarding rubber material properties due to tyre industry opacity, or maybe because of the high cost associated to rubber material test. And in this case, the approximation to have a good correlated model change, and we use a finite element model, simplified dynamic model for this task. And these models are directly correlated using the results of the component test. An optimization process is done in two different levels, hyperelasticity and viscoelasticity, to match the component test results. These tests can be modal, stiffness, or frequency response, depending on the correlation level and the tyre performance to be studied. So we can see on the right side, for example, the calculated frequency response of a tyre model, where the main objective was to calibrate the frequency response of a static tyre up to 300 Hertz. We can see there the peaks of the point mobility radiation in the radiation direction, which show the frequency, the most shapes of the tyre at that peaks. And we see in above the, for example, in the force transmissivity in Z direction, the cavity noise resonance. So until now, this presentation was focused on the capabilities, but a very interesting part for you also is the experiences that we have and the case studies that we had by applying this knowledge directly in the real development process. And these case studies will be shown in the next slides.
Okay, thank you, Carlos, for your explanation. So, as you say, very important thing in this presentation are the case studies. So, some experiences we have here in IDIADA. So, as explained before, the test we are performing here helps the customer to integrate the tire on their vehicle. One of the application is the selection of tire for braking performance of a vehicle. Customer can give us a set of tires or different tires to compare them on longitudinal condition, on dry, wet, or both. With those measurements, theoretical stopping distance based on tire maximum longitudinal adherence and characteristics of the vehicle is calculated. With this data, a classification from the best to the worst on each condition is defined. This classification will help the customer to understand better the performance of each tire for the specific test condition.
Another experience we had in the past was regarding a high fidelity comfort assessment in our new driving simulator. By means of generating an MBS model and including an F-tyre in real time, the main objective was the prediction during vehicle development phase of ride and comfort performance. As I said, we used an MBS model and an F-tyre in real time. We also included the usage of our virtual proving ground, and we integrated everything in our driving simulator. The main objective was to obtain, throughout our simulations in the driving simulator, the same human feeling as the driver would have in real conditions. And due to our high fidelity MBS model and F-tyre model, we could have good conclusions on the ride and comfort behavior of the vehicle and the tires. And this technology permits us also driving evaluations during the vehicle development while the vehicle is not constructed. Another important experience we had in the past was developing an endurance test mode for high performance tire. The starting point was testing a sports car in a circuit, and the main objective was to translate all the inputs that the tire suffered during the circuit handling to a laboratory testing methodology. As I said, we ran in a circuit with the sports car. Once we had the inputs on the vehicle, we did a complete vehicle characterization, including KNC test, moments of inertia, aerodynamics and powertrain. Also, components were characterized, such as brakes, suspensions, and tires. And we included a magic formula model from we could extract and calculate all the tire inputs that were occurring in the circuit, and with all these inputs we could translate it into a laboratory durability test method. What we obtain of all these simulations and testing was a very representative durability test in the the real driving conditions that the vehicle was driven.
So in this case, the idea was to perform a sensitivity analysis of the tire structure, involving in this sensitivity analysis the rubber section and the nylon plies for the three stiffnesses of the tire. So the variables selected here are the rubber edge shortness of the tire section and nylon cap plies, stress strain curves, and the study is performed with help of a design of experiments. So the results obtained show that how carcass and other sections of the tire influences each of the stiffnesses respectively. So next slide, Emmanuel, please. So next case study was the correlation of a model for fatigue and noise prediction purposes. And in this case, the objective was to correlate the tire dynamic response of the tire until 300 Hertz by means of model test. The model was simplified by means of connector elements, and as we see after the optimization loop until 250, 300 Hertz, the results, the results are matching the simulation are matching the test results, and the correlation was good, and model was ready to be included in the whole vehicle model. Besides, we obtained a lot of information about the influence of each tire section in the tire mode, shapes, frequency. So, Emmanuel, please. Yes, and the last case study is an ongoing project of our PhD research engineer Bharat Anantaramaya, with the main goal of developing a powerful numerical tool that facilitates the prediction, propagation, and perception of tire noise. For this, Bharat is performing modal acoustic and static tests for the tire performance understanding, is also developing a virtual tire for noise prediction and a methodology for psychoacoustics and annoyance evaluation. A subjective evaluation for synthesized noise can also be done, and as well as studies on how changes in the tire structure affect the synthesized noise. So this is, for example, a synthetically created noise. Emmanuel, please. Okay, this was synthesized noise. And now we will present some testing modeling topics that we are working on right now. So we can, again, if you want, Emmanuel. Okay, this is just an example. And yes, we will present now some testing and modeling topics we are working on right now.
So, as we explained from the first slide, tire development needs a continuous improvement process, as it's a very complex product. For that, some projects are ongoing to permit a better understanding of the tire, like the following one. So, the integration of tire 3D scanner or moment of inertia test rig in our process to have more information about the tire and have a better information for the models. As explained before, we are working also on the integration of the block of asphalt on our KLC test rig to have same condition as on proving ground for quasi-static test, but also the integration of a rigid rim on F-tire models. So for that, we are working on the implementation of a very rigid rim on our test process, and of the characterization of this rim. And the last project is a development of a tire stiffness rig, which can permit us to have better and more results than we have now.
Regarding our future modeling capacities, we are studying the possibilities of including new models in our products, such as Magic Formula 6.2 or Swift, also CD Tyre. We are also studying the possibility of integration of flexible rim in F-tire, and we are developing some tools for noise predictions through FEM or BEM methods. As a wrap-up to point out our conditions, all our in-house testing and modeling in real proving ground conditions. Also our complete test catalog of magic formula, tyre and FEM models. And last but not least, we would like to point out our adaptability to our clients' needs. Also, we offer the possibility of supporting our clients during tyre or vehicle correlation phase. And we always like to have a close partnership with each of our customers. So thank you everyone for attending the webinar. Now feel free to write your questions in the questions and answers chat, so we can answer in a few minutes all of your doubts.
Yeah, thank you, Imanol, and all the entire team. We have already some questions that we could start answering while anybody else could write down some other questions. The first question, I think, is for Carlos. It says, during the modeling and simulation process, are you using your own property tools or those provided by Clitex Modelica? In addition, do you run co-simulations for function development?
Okay, well, we are using the tools that we are using are commercial softwares, okay, and there are several commercial software that allow you to build a FEM tyre model in this case, in my case. And for the question about the co-simulations for function development, we have performed co-simulations of FTyre with Abacus Explicit in some occasion, and that's all our experience in this kind of topic in the co-simulations.
Okay, we have another one which is quite specific. It says, in the slide tyre models for vehicle development, what is the full form of FRF? In addition, what is the scale for the I-axis, the inheritance?
Okay, this is also a question for me. I think in this slide there is just an example of which kind of diagrams or graphics we use for doing the whole procedure for calibrate the FEM model. In this case, was just an example, not specific. But what we use there are vibrations, accelerations, basically.
Okay, we have another one. The question is, which part of the proving ground test pattern are being used as the correlation validation for the tyre model characterization?
Well, if I understand correctly this question, we normally perform our testing in a high-speed track, both vehicle and component test.
Okay. The last that I have right now, do you also take into account grooves present on the tyre surface while modeling it?
Well, if we perform a basic F-tyre model, we normally do not include the grooves, but we have some experiences including this characteristic of the tyre. And regarding FEM models, the grooves are always present in all our models. All our FEM models are high fidelity models, which include all the geometric and construction characteristics of the tire.
Okay, the last question that just arrived now is where I can get your presentation. This presentation will be public in YouTube. We will publish. And of course, in case you would like specific information about what we can do, you can send an email to this email address, and we will be pleased to answer your specific request. Okay. Let me see. Okay, now some more questions are entering. Just a second. I lost a little bit. Yeah, we have another one. It says tyre noise prediction is pattern-specific noise or covers the complete frequency spectrum. Carlos, I think it's for you, that.
Yes, this is for me. So actually, we were focusing on tyre rolling noise until 350 hertz, and now we are also working with models that can cover until 1,500. So we are also taking into account the tonal component of the randomization of the tyre, and that's all until now. Yes, until 1,000 hertz, 1,500 hertz. But we are not covering all of the phenomena that are producing a noise in the tyre. We are concentrating on the tyre surface interaction and basically and the structural borne noise that is following the path into the vehicle also.
Thank you, Carlos. I think we'll have one for Pierre. Up to which speed can you perform the test with the trailer on the test rig?
Yeah, so for skid trailer on proving ground, we are able to go until 120 kilometers per hour. But there is a point to study depending on the tire you want to test. And concerning the drum machine, we can go.
You have a new one. See yes, data or temperature sweep testing. Any one of them is sufficiently model viscoelastic material model. I think this is for Carlos. Maybe if it's too specific, we can answer.
This is a very specific question we can answer.
Yeah.
With yes.
I will propose that I cannot say names. The one who has asked this to send an email to this email address, so we can have some discussion, because I think it's really specific. This. Another question regarding fan time for road noise. Do you consider the rotating effect like gyro?
We are considering some kind of rotation of the tire, yes. And this is what we are working on actually with the PhD of our colleague Bharat, and yeah, we are considering it, but until now we were focusing on static tires. This is something that we are developing right now.
Okay. Right now, I don't see any other question coming.
Well, there is another question in the chat.
Yeah.
That says, in the validation of modal analysis, I could see a good level of correlation between the test and simulation, almost at all frequencies within 300 Hz. What material model did you use to capture the material damping? think Carlos could help with the answer of this.
Maybe this is also a very specific question, and we can answer directly if you agree by mail.
Yeah, I think there are entering in the chat some questions. Yeah, regarding temperature effects. I think these are quite interesting discussions that maybe in a webinar it's too specific, no? Because here I have a question regarding how to consider the temperature. I mean, this is kind of questions that I think it cannot be answered in some minutes. I would strongly recommend to redirect all these questions to this email address, so we can go through all of them and discuss a little bit what you have on mind, because it's also difficult to answer these kind of issues in the small time that we have. Okay. I don't see any other questions coming. So yes, a new one. Do you have any in-house method to filter out only the tyre noise from all noise sources in a running vehicle? Yes, I think we have something. The issue in this question is that we don't have the responsible for this kind of data post-processing. We have a team that taking charge of noise testing. Unfortunately, we don't have it in our team. The people that are involved are specifically for the things that you have been asking during this. You have been presenting to this webinar. We will take note of this question and we will come back to you. Okay. But yes, for sure, we have a capacity for making a capsulation of noise for analyzing the running vehicle noise. A new one. Is the good fit in between test and simulation in the F-tyre reached without flexible ring usage? Which is this frequency? Well, maybe the frequency, I don't know, but could you please see my...
We are studying the test. We come any of our class. We are doing it, and yes, of course, we obtain a good fitting between the test and simulations with our tyre. And which is the frequency? Well, we fit our models up to 250, or more or less in this range. Our tyre and simulations are good fitted.
Okay. Well, I have another question. What time for next meeting? We are going to do another meeting at 5 Spain time for another market that we will present the same, but for another part of the world. So I think that today most of you are from Asia, so it's a reasonable time for you. During this afternoon for us, we will do another presentation. Here it comes one. Is there any apparatus which could measure the size slip of each tyre in real life, or they still have to be derived from other vehicle dynamics parameters? I guess that this question comes if we can register the slip angle in vehicle conditions.
So from our side, we are not testing the tire on vehicle because we are testing tire as a component, but not as a part of the vehicle. But using, for example, a co-revit system, I think you can mount it directly on the wheel. You have the direct slip angle of the tire. So I think it's possible.
Thank you, Pierre. We have another one that came through the chat. On one of the initial slides, you show a chart which the y-axis is stability after peak slip angle. How do you measure this? Or can you explain what this metric is?
Yeah, so basically what we are naming stability after peak slip angle is to compare different tires, so it's not a very quantitative metrics, but more to compare. So we are talking about how much forces is losing the tire on lateral behavior in this case after the peak, the maximum peak of forces. So we define a slip angle, maximum slip angle, and we measure how many forces is losing from the maximum to this point, and we compare the different types.
Thank you, Pierre. We have another question. Are IDIADA FEM models of tire belonging to the group of F-tire models or Pacheco models, or they create third independent group type of tire models? Carlos, you know?
I think, yes, I think Emmanuel mentioned this already. So the FEN models are very complex models that are different from F-tire or Pacheco models, in which we can modelize the geometry very good, and all the material parameter or material characteristics of all the section of the tire. So they are a completely different kind of model.
Thank you, Carlos. I think I have a new question for you. What friction model is used for the finite element model?
Well, it depends which performance are we studying, but normally we use constant or variable friction coefficient. I mean, they can vary. For example, for some handling calculations, we can do that the friction coefficient can vary depending on how is the surface of the contact surface between the tire and the rod in the handling calculation. But sometimes for other models we use directly constant values of the friction coefficient.
Thank you, Carlos. Well, right now we don't have any other question. Maybe we can leave a couple of minutes if some of you would like to have more questions. In the meantime, well, I just wanted to remind that we will be pleased to send to get in contact with you in case you have further questions, and we can discuss for any need that you may have in the future, and what to be able to support you in any that you may have, any need that you may have. So it looks like no other questions are entering.
If you have further questions in the future, you can contact us directly in this email. So feel free to contact us, and we can have open discussions on these topics.
Okay, so yes. Well, I see that no other questions. Just I would like to thank you your kindness to say thank you to us. We'll be pleased to support you then. If we don't have any other question, of course, well, we can continue speaking in the future by this. We can leave the webinar here. Then looks like nothing else is entering. Thank you very much. And I hope to see you one day, any of you, and I think some of you will surely get in touch in the future. Thank you very much. It's been a pleasure, and thanks to our team.
Thank you.
Thank you.
Thank you very much.
Bye.
Bye.
Bye.